see what I can do. All right, guys. Good to see everyone again. And let me kind of clean this up. This should be probably maybe the last major thing, last major video you're going to see on this type of review that I'm doing right now. Let's see how the whole thing plays out. Let me see here. I don't have. I got my other glasses here, which are not quite as good, but they're gonna do for us. You've seen all that we've done the last time that we were together. The set. This is, like I said, this is probably like the last video for this kind of old review. So I think we've done up to this point. We've done everything that I want to do, or very close to it. All of the major stuff I did. Let's just hook it around and do some like selected problems from the practice exam for the final, the old practice final exam. And let's look at some of the stuff from the old practice exam number 3 as well. When they tell me how they want this course taught, it's gonna be exactly how they want it done. There's gonna be some disparity to this. Now, you heard me say this numerous times over the taping of all these videos. Math is math. I don't care if it's the old practice exam that I'm dealing with right now. The lectures that I'm doing, the things I'm showing you how to do are the math you're going to find in any basic algebra textbook. If you're looking to use this for physics, for chemistry, either here at MATC or elsewhere, so I'm going to post this at UWM as well. I was given permission to do so. Either at UWM or MATC or anywhere else, because I'm making the video and stuff like this, they allow us to put it pretty much anywhere we want, to post it for people, for them to be able to look at. MATC and UWM right now, as I'm speaking, is going to have access to it. From algebra to physics to chemistry, from MATC to UWM to UW-Madison to UW Parkside to Harvard or Yale. I don't care where you are. From Greece to Russia to anywhere, to China to anywhere, guys. Math is math. This stuff's going to help you out. So always look at it from that perspective. Be optimistic. Let's see what we can do here, guys. They gave a few problems on old practice exam number 3. So I'll kind of like write it that way if you don't mind. And these glasses are less than good, but let's see what we got here. There's a lot of ways you can write stuff and get out of the woods, so to speak. So for number 3, old number 3, as we said, right? Let me take a couple selective strikes at it. Let me work with old number 3 for now, and I think it kills a whole bunch of birds with one stone. Let's do problem number 2, and we're talking about the square root of. Forgive me, not the square, the 6th root of x to the 48. You got to be able to do all the manipulations, guys. I mean, you got to remember a lot of stuff. If you take the nth root of something, if you take something to the nth power and you take the nth root of it, you get the original quantity. If you take the original quantity and then get the nth root, and after all that, so the nth, something to the nth power, the nth root of that quantity is x, or you can take the nth root of x and take it to the n, you get this. Period. How does that work? It works a lot of ways. If you got this, and you got it to the 1 over n, I'm just drawing what this is in terms of exponents. If you exponentiate an exponentiated quantity, you multiply the exponents. 1 over n times n is n over n is to the 1 is equal to x. So the laws of exponents are consistent with what you're doing. On the other side of this thing, if you take this to the 1 over n and then go to the nth power, you're still getting this, which is still this, which is still this. So basically, you can mix and match those. You can switch them around, and you're okay. Okay. So on and so forth, guys. Hopefully, this is old news to you. I hope it's old news to you because it should be old news to you. Problem is I'll write this in the right place here. X to the m over n is the same as, you can play this a whole bunch of ways now, guys, how you want to do this. I mean, you could say that's x to the 1 over n, the whole thing to the m. That's the nth root of x, the whole thing taken to the m. All these are equivalent to one another. Have them in your bag of tools. Have this in your bag of tools to be able to get the job done. Now, you've seen this. Like, as I said, this should be old news because you have seen me do this. Switch them around. What does that mean? It means this. And at the end of all that, you do this. These are all equal to each other. This, that, and that. All of them, all the thises are equal to each other, all the that's are equal to each other, and all the thises and that's are equal to each other. All 6 of these items are equal to one another. All 6 of these items are equal to one another. So on and so forth. How are you going to do this? Well, they're kind of particular how they want it. I mean, that's just it. They may want to ask you, hey, give me the answer in terms of radicals. Give me the answer in terms of radicals, or give me the answer in terms of exponents. They may want one or the other. That's something they'll give you a heads up on. I mean, we're not going to leave you out in the woods like that, so you're not really sure what they're asking you. Is it true that x to the 48, the negative, leave the negative alone. It's the negative's in front here, the negative's in front there. Now you can just forget about it. Pretend it's not even there for now, while always remembering that it's there. Okay, if you allow me to say it that way. This whole quantity to the 48 is the same as this whole quantity. That's what it is. The 6th root of x to the 48 is x to the 48 to the 1/6 power. If you exponentiate, whenever you're exponentiating exponentiated quantities, you multiply exponents. 1/6 of 48, you're done. It's that simple. Let me just see how they're trying to. And some of the some are easier than others, I guess, when you do some of these. Let's look at a problem like number 3. If you got something like this. Again, guys, even for those of you that are like taking the physics classes, the chemistry class, the engineering class, and say, well, why do I need to know this? It's good to have that. The more strength you have in your repertoire, the more you know the mathematics, the more opportunities you have to see what's going on in a more intuitive fashion, which allows you to be more creative in your problem solving. You're never going to lose in any technological field. You can go into economics if you want. You can go into, you're analyzing statistical data, Gaussian distributions that occur in physics and economics, engineering, you name it, so on and so forth. The more mathematics you have, the more strength you have to attack modern technological science. That's why this sort of basic algebra is going to be good for all of that stuff. Whether you're going to Harvard or whether you're going to UWM or whether you're going to some university in another country or whether you're going to MATC, we're all in this together. The math is the math. If you know what you're doing, you know what you're doing. There's brilliant people at MATC. There's brilliant people at UWM. There's brilliant people all over the world who have gone to school or not gone to school. And I guess the more you know, it's not going to hurt you. If you know the mathematics is always going to be something helpful for what we're doing here. If you got this, they're pulling this on us. You can play this a whole bunch of ways. To bring the 1/4 inside, you bring the 1/4 inside. That's the 4th root of 1. That's the 4th root of 256. The 4th root of 1, what number times itself 4 times will give you 1? It's 1. The 4th root of 256, you can play this a bunch of ways. I'm probably going to go a little further than I need to go. You can simply find the 4th root on your calculator. You can write it a whole bunch of ways. I mean, you could say 256 to the 1/4 is 256 to the 0.25 power. That's going to spit out a 4 at the end of the day, you guys. you kind of maybe, here's kind of another look for you. Is 16, let me see if I can manipulate this and kind of get a gut feeling for what's happening. Is 16 times 16? Is 16 times 16 256? Sure is. All right, I think I know what's going on here. 16 is 4 times 4. 16 is 4 times 4. 4 times 4 times 4 times 4 is 4 to the 4th. The fourth root of 4 to the 4, I mean, where do you want me to stop on this, guys? You got 4 to the 4 right here. You get the fourth root of that. You take that to the 1/4. What's 1/4 times 4? It's 1. 1 times 4 to the 1, that's 1 times 4. Obviously, about 4 steps ago, I could have been done with this thing. I'm just trying to show you the mathematical logic that's present, regardless if you've taken a shortcut or not. Regardless if you've taken a shortcut or not. Looking pretty good. So you're getting that as a final answer over there. They give a couple interesting ones here. 5 and 6. I don't know if I'm going to do them both. I got a feeling I'd like to do both, to be honest with you. Let's look at 5 and 6. Old number 3. Okay, guys. So let's think. Let's think a bit. See how they want to do this. I mean, they may have, there's not a lot of consistency in how this can be answered. And that's not a slam on the people that made the answer key here. I think their hands kind of get a little bit tied when they do this kind of stuff. Yeah, here they left it without radicals. I could do both answers for 5 and 6. I could do them with radicals and only with radicals. I don't know how efficient that would be. I got some feelings that there's many ways, well, I don't know about many, but there's numerous ways that you could write the answers for 5 and 6 that I'm about to do. The way they played it is they usually just want positive exponents at the very least. And then at the end of all that, leaving positive exponents only, they gave positive exponents and they left it in exponential notation. They did not use radicals when they did this. So what we got here is 5 and 6. I want to do both, actually. And I'm going to give the answer the way they gave it, and that's it. I mean, we'll try to be pretty straight up with you on stuff like that. I'm not going to hold you accountable for something where you don't know how to give the answer. It's like me saying to you, how much money is left in this particular scenario, in this word problem, and then you give the correct answer of $200, and then I say to you, actually, you're wrong. The answer is not $200. It is 800 quarters. Yeah, 800 quarters is $200. You had to write 800 quarters. I'm not going to do that to you. We're not going to do that to you. So with this in mind, let's see what we got here, how you write a problem like this, how you actually do this stuff. Now there's a lot of tricks of the trade here, guys, and I'm going to use whatever I need. I cannot rederive these. You're going to have to go back to my other videos and look at what I've done as far as some of the logic that takes place. I'm just going to mention the logic that needs to be done, and you can see earlier that I have a derivation of that in an earlier video somewhere. Okay. As you look at this, how would you pull it off? Well, I'm going to leave everything in exponential notation. I'll tell you one thing that first comes to mind here in this whole process. If there isn't, they want only positive exponents. And so let's see here. Let me just see exactly how they do this. They're looking at this, right with only positive exponents. So yeah, they want positive exponents. Take this guy, pick him up, and move him north. Anytime you cross the line, the sign of the exponentiation changes. every time you cross the line. Cross the line, the sign of the exponentiation changes. I've already explained that. I did explain it. I don't know if I ever explained it with such an elaborate exponent. Usually it's what x to the 3 or x to the negative 3, that kind of thing. But it happens with all exponents. There's a negative exponent present, and you cross the line, either going south or going north. The negative exponent will become a positive exponent if you cross the line, whether you're going north to south or south to north, whether you're going up to down or down to up. If you're crossing that line, that's how it happens. That's how the trick all works. You've got this. And like I said, there's a number of ways to do it, but let's play the game the way they want us to do it. We've got this right here. Forgive me here, guys, as we do the whole process. I didn't have to make the move that early. I could have left things as is, but right now they have this thing right here. Now, you will bring the 1/2 inside. It'll be 81 to the 1/2. That means the square root of 81. That's 9. Then you'll go 2/5. When you're exponentiated quantities, you're multiplying exponents. So here's 2/5. Here's 1/2. I think everybody knows where I'm going here. This one's 8 over 3. That's that. And there we go. Let's see where this thing's going to go, you guys. 81 to the 1/2 means the second root of 81, which is 9. 1/2 times 2/5 is 1/5. 1/2 times 8/3 is 4/3. A half times 7/5 is this. I've got a feeling they stopped right there. I mean, there's more elaborate stuff you can do here, man. We could do it. I don't know if I want to go there. I mean, there's ways I could put this underneath one radical. There's a 5 here. There's a 3 here. What's 1/5? 1/5 is the same as 3/15. What's 4/3? That's the same as 20/15. Then I have to double it. So 3/15 is 6/30. 12/15 is 24/30. Forgive me here. It's 40/30 rather. And this right here would be 21/30. I get everybody to the 30th root, and I can put everybody underneath one root. I don't know if I want to go there. They're not going there. Maybe I should go there this one time, just to give you some kind of feeling here for maybe the ways this stuff can get looked at. There's a lot you can say. There's a lot you can, how far do you want to take this thing? That's always the question on a lot of this stuff, where you could go. Let me just see how they gave this answer. Let me just see it again. I think they stopped there. Let me just go this one time, kind of the extra on this thing, to kind of give you some sense of what's happening here, about the mathematical logic that is present. You're never going to know all the math, guys. Nobody is. I'm not, nor are other people far more brilliant than I am going to know everything that there is about mathematics. There's always something to know. They pretty much stopped right here. They gave you this as the final answer. We can take that. That's fine. That's the final answer. That's the way they wanted it. Let me kind of play devil's advocate this one time on this one and say, okay, for the heck of it, is there another way, there's another look you could have given this thing? Well, I'll tell you what. Here's a 5, here's a 3, in the denominators now. The denominators of the exponents. In the denominators of the exponents, there's a 5, there's a 3, there's a 10. What is the least common denominator? What is the least common denominator of the associated with all this, guys? In other words, a 5, a 3, a 10. 30. 5 goes into 30. 3 goes into 30. 10 goes into 30. It's the least common denominator. Tell you what I'm going to do. We got a 9 here. 30, huh? Is 6 over 30 the same as 1/5? Is 40 over 30 the same as 4/3? Is 21 over 30 the same as y? What's going on here? Well, 9 is 9. He's not really in the mix. Tell you what I'm going to do. The way it's looking right now, I could take x to the 6th, z to the 40th, and right here, take y to the 21, and then exponentiate to the 1 over 30th. This thing could play out as 9. I'm not saying you got to go there. The 30th root of x to the 6th, z to the 40th, y to the 21. Among other ways you could do this. This guy's out, like I said, this guy's out of there. He's not in the mix. Just got this. 9's going to be multiplied with that. Nobody went there. This ain't a bad place to go. There are a lot of ways you can do this. So, Bill, what do you think? Is that okay? Okay, all right. So it's looking pretty good that way, you guys. So if that's the case, not too bad. Not too bad. We don't need to go there, but it's good to know how to go there. The more you know, the more flexibility you have. The analogy that I've given to all of my students over many years, if you look at the great basketball players that have played the game, the great athletes that have done things, great wrestlers, great sprinters, great football players, great basketball players. The great basketball player can do the slam dunk, but he can also hit the three-point shot. He can also play the great defense. He or she can play the great defense, can do this, that, or the other. The more flexibility you have, the more versatility that you have, the more ways you can attack a problem and less chance of being fooled. That's applicable in any field, whether it involves mathematics or not. Within mathematics, as I said, physics, chemistry, math. The more you know, you're not going to lose. You're not going to lose. Okay. By taking a slight break here. Okay. I'm taking a slight break. I'll be back to you guys in 1 second, and we'll take it from there. Okay. Thank you very much. All right, guys. Let's keep going. We got a lot of busy. We're all very busy these days, and so we're doing this right. We're going to get it done right, and we are doing right. I'm getting a lot of great help. So let's keep going. You saw me handle from old number 3, problem number 5. And I went a little further. You saw me do that, right? And you saw that, and that's all right. Nothing wrong with that. Let's go this other one. Number 6. And kind of see what we can say there. So number 6 is, I think we're saying it right, guys. Let me try to. Sure I got this thing right. We got 16 z to the 4/3 x to the negative 2/5 y to the 7/5 you got this. At this point, it's old hat. You bring this guy up here, and you take it that way. Now, let me see. Man, it looks a whole lot like the stuff I did before. The reason is I didn't write it down right. That'd be one explanation why it doesn't look right. Let's see what we have here. We got something looking like this. So how are you going to do that one? You're going to do it same exact way on something like this. So let's see here. I think we did for this one. For some reason, I'm not trusting some of the ways I wrote that. I think there was supposed to be a 42 on there. Did I write a 42? Unfortunately, I erased it, guys. Let me, just in case, erase this. I don't have access to the recording right now. Let me do 5 and 6 relatively quickly. Let me do 6 right now. Let me show you the way they want it done. Let me go a little bit extra. when we do it. I got, for some reason here, I'm thinking, I think I may have made a small mistake on number 5 with it. So I'm going to do 5. I'm going to do 5 again, just in case, you guys. And regard the way I do number 5 the next time as the way you want to go with this. Look at this right here. Take this guy, cross upward, and let's see what we got. We got 6. We got x to the 2/5. We got z to the 4/3. We got y to the 7/6. We got this right here. Multiply, take the half in there and bring them in. There's 16 is the same as 16 to the 1. In a sense, distribute the exponentiation. I don't like to use the word distribute when there's multiplication and or division going on. I just don't like doing it. But in a sense, in a pseudo sense, you can take the exponentiation that's on the outside and bring it to the inside and multiply. Remember, when you're exponentiated quantities and there's multiplication and or division going on, you're multiplying the exponents. 1 times a half is a half. 16 to the 1/2 is the square root of 16. 1/2 times 2/5 is 1/5. 1/2 times 4/3 is 2/3. And 1/2 times 7/6 is 7/12. Okay? The square root of 16 is 4. Here's x to the 1/5. Here's z to the 2/3. And this is 7/12. Looking good. Looking good. This is the way they're answering it. What did I tell you guys? Well, let me make sure I told you guys right. First of all, we're doing it. That's 2/3. You saw me kind of do it. My procedure for problem 5 of old practice 3 is fine. There's nothing wrong with the procedure. I think I made a typo there somewhere. Trying to hold my memory here. We erased some stuff because we had to piece together a couple videos here. So I erased it, so I don't have it in front of me. But let me just err on the side of caution and do 5 one more time for you. Before I do 5 one more time for you, let me stop right here. That should be the answer. And the way I did 5 and the way I gave the answer to 5, the way they were giving it, I think it was spot on the mark, right on the mark. It's just the way I did the radicals later that's something that concerns me a little bit. So let's have a look at what's happening here. This is 1/5, this is 2/3, this is 7/12. There's a 5 in the denominator, a 3, and a 12. All denominators are the following: 5, 3, and 12. How about 60? 5 goes into 60, 3 goes into 60, 12 goes into 60. I'm going to go that way. For the record, and this is the way they're giving the answer, and you're done. This is the way they gave the answer, you're done. If you're going to get a little fancy about the whole thing, is 1/5 the same as 12 divided by 60? Yeah, 12/60 reduces to 1/5. Is 2/3 the same as 40 divided by 60? Yeah, 40/60 reduces to 2/3. Is, that was a z right there. Is 12 on the bottom the same as putting 60 on the bottom but making the top 5 bigger? Is 35/60 reducing to 7/12? Sure is. Here's 4. You can take x to the 12, v to the 40th, and y to the 35th. Y to the 35th, and take that product and quotient to the 1/60th power. That's interesting. You can write it as x to the 12, z to the 40th, forgive me, I just want to put the radical in there right off the bat. 1/60th, huh? That's the 60th root. To the 1/60th power is the 60th root. Here's 4. Here's kind of a fancy way to look at it. The 4 is on the outside of that. And there you go. That's kind of what I was doing with 5. I just suspect I guess you'll see it on the tape. It's on the tape. We're not gonna lose a whole lot of sleep on it. Because I think with 5, I did actually get to this one the way they wanted it. I suspect I put a 21 somewhere where I should have put a 42. So let me correct that right now. So that's 6. That's 6 right there from old 3. Let's look at old 3 again. Let's look at number 5 one more time, you guys. I think it's just worthwhile. How we're doing a lot of these tricks of the trade here with this stuff. Erase all of this, give ourselves a little bit more room. You guys have access to all this. So let me, give me 1 second, guys. Something just came up here. Whoa. All right, guys. Let's see what we got here. Okay, guys. Just play it safe here, guys. I'm sure I don't have the luxury of seeing what I did here. I erased it. There's things that go on, guys. This is actually a great service that people at MATC are doing, and the gentleman that's actually helping me, and other people that have helped me in other locations as well. So it's very good. Given the circumstances that are transpiring, it's always going to be it's going to be less than ideal. Nobody's fault, but the help that we're getting is amazing. To actually get this done, and that's for sure. Sorry, these glasses are also not the best, so I basically got to glue the paper to my face to be able to see what's going on. Let's just one more time do this. They say repetition's the mother of learning, so let's go for it. I think the way we had done it the first time, to give the answer the way they're giving the answer in the end, that was correct. So that's not really changing. I just want to be a little cautious on some of the stuff I've said here, guys. The procedure, regardless of a typographical error, the procedure is on the mark. But technically, the way you want to be giving the answers always in anything that you're doing, you got to do it completely right. You may be largely right, but still get the wrong answer. Your procedure is totally right. They still got, a lot of times, a lot of evaluations, it's either right or it's wrong, and that's it, period. That holds for me, that holds for everybody. So I want to make sure this is completely right for you when you're looking at it and the different ways I've shown it. When you're looking at something like this, you guys, you want to take this and cross the line and go upward. So what you have is you got 81 x to the positive 2/5, right? Z to the 8/3. And we got this. The whole thing's going to be taken to the 1/2. So what have I done? I've done what I've done at this point a number of times. If you're moving something and crossing the line, the sign of the exponentiation is going to reverse. I want the sign of the exponentiation to reverse because I don't want negative numbers there. So when you cross and go upward, you get a positive exponent. As you do this, bring the 1/2 in there, and you got 81 to the 1/2. That's the square root of 81. Then you got 2/5 times 1/2. Whenever you're exponentiated quantities, you are multiplying exponents, provided that there's only multiplication and or division going on within the quantity that's being exponentiated. If there's addition and or subtraction going on within that quantity, all bets are kind of off. There's other techniques that have to be employed to do some sort of simplification. That's another story. That's just another story. Some beautiful theorems out there that get us to places that will help us out, I guess. That's not our business right now. If there's multiplication and or division going on only within a quantity that's being exponentiated, then you can distribute the exponentiation everywhere throughout the product and or quotient. Everywhere where there's multiplication and or division going on only, everywhere where there is a factor, anywhere where there's anything in that dynamic, you can bring the exponentiation inside and you multiply by the outside radical. You multiply by the outside exponentiation throughout what's inside if there's multiplication and or division going on only. As we go here, 81 to the 1/2 is 9. Take that out of there if you want. Half of 2/5 is 1/5. Half of 8/3 is 4/3. You can write this a bunch of ways. Half of 7/6 is 7/12. For some reason, it should not have been that. It should have been a 5 right here. Okay, you can see, you go to correct an error, you make another error, right? Or a potential error. That's 7/5. That's 7/5 right here. So yeah, we were getting the right answer the first time. So if it ain't broke, don't fix it. 1/2 times 7/5 is 7/10. It is what it is. I mean, it is what we got here, guys. So you got it to here. I think that's where they let it go. And I know that's what I gave the first time. That's fine. That's the way they gave it. That's the way that they gave it. The way that they gave it. Now, is there another way around this? 5, 3, 10. Least common multiple there is 30. The least common denominator with all those denominators is the same as the least common multiple. It's 30. Are you telling me you could write this thing as, I think this is where, for some reason, no, I think I did, you know what, guys, I don't know what the heck. For some reason, I'm trying to look at it, and I think I'm looking at it a bit too, make sure we got this right. This looks fine. This looks fine. I think I'm worried for nothing. Well, if this does you any good, you're seeing it again. I got a feeling it was straight up on the mark the first time. I'm just, for some reason, I'm trying to figure out why that went the way it went. Right. 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 So, yeah, everything's fine. I didn't think I need to do anything, guys. I think, well, I mean, repetition's the mother of learning. You're getting some here, I guess. 1/5 is 6/30. 4/3 is 40/30. And 21/30 is 7/10. 40/30 is 40/30 is 4/3. 21/30 is 7/10. 6/30 is 1/5. Sorry, guys. I got a feeling I can't remember what I said the first time, but that's okay. Let's err on the side of caution on this one. Repetition's the mother of learning, as we said. You can go right here if you want. Go here. Take the whole thing to the 1/30. The 30th root of x to the 6th, z to the 40th. All right, let's forgive that, but why not? It's there. They talk about different things that work. I mean, the different things you can do. Let's look at the same practice number 3. Again, old number, this is all old number 3. Old practice. Number 3, as we had set out earlier, right? So it's still here. If you had something like number 7, they generally don't like, they don't like a radical. They don't like you to have a radical in the denominator. That's kind of the convention on it. Now you could probably argue that with me. Go, yeah, Milos, what's the point here? This thing has essentially a radical in the denominator. There's stuff you can do with this, and there's stuff you can do to undo it. This is okay for what we're doing right here. Technically, this could be taken a lot further. Let me not go down that path. I don't think it's going to help you that much. But technically, there's more that can be said right there, you guys. Here, let's do that more that can be said. It's a little easier to look at. The radical of a quotient is the quotient of the radicals. If I multiply both of these by a special one called the square root of x over the square root of x, square root of 81 times the square root of x over square root of x times square root of x, which is the square root of x squared. Wait a minute. Isn't the square root of x to the 1/2? Doesn't that imply that the square root of x squared is x to the 1/2 squared? Don't you multiply exponentiated quantities and get x to the 1, which is equal to x? They don't want a radical on the bottom. So here, the square root of x squared is x. The square root of 91 is not, the square root of 81 is 9, and the square root of x is the square root of x. They don't like a radical in the denominator, and that's how you do 7. For a problem like 8, old practice exam here again, guys. Here's some of what they're talking about regarding that. right, guys, still old practice number 3 on this. I'll tell you otherwise, you know. If it is otherwise, whenever it's otherwise. If they gave you a problem like problem number 8, all right, guys, you're given something like this. They don't want radicals in the denominator. So what they do is put parentheses here, put parentheses there. What is the conjugate? Not complex conjugate, but it could be a complex conjugate too. You saw me do that with the complex conjugates some time ago. Okay, you got to integrate all these together. There's like 300 problems here, guys. I can't do all of them, but I've shown you how to do all of them. Okay, I've already shown you how to do all of them before this video. So you've got the data that I've given you, that I've posted. Look at that. You'll be able to do it based on stuff I've told you. There's a lot of stuff to listen to, but and you don't have to listen to it. If you're comfortable with this stuff, you don't have to listen to what I'm doing right here. Okay, that's your call, but it's there for you in case you need it. Okay. For this right here, I got to get a copy. You know, a good way to get rid of square roots is multiply by other square roots. I want you to remember something. Isn't it true that the quantity a minus b times the quantity a plus b is a squared minus b squared? Yeah, I think that's going to help us out. If this is a and that's b and that's a minus, why don't you make this a? Why don't you make this b? Let's see what we got. This times this, well, we'll definitely cross that bridge as we need to cross it. We're doing good. The bottom stuff, if this is A and this is B, and once again, this is A and this is B, a squared minus b squared. A squared minus b squared. You did this. You engineered this. You engineered this so that you could get out of the woods. What do you got? Well, I still got this. This is like a plus b times the quantity a plus b times the quantity a plus b. The square root of 13 squared is 13. The square root of 2 squared is 2. That's how it gets you out of the woods. Now take this guy and go over here and go over there. You got the square root of 13 squared, we know how that is, and we got the square root of 13 times the square root of 2. We'll get into that in a second. Then you're going to go here. Square root of 2 times square root of 13. And then you got the square root of 2 times the square root of 2. And on the bottom, you got 11. Square root of 13 squared is 13. Square root of 13 times the square root of 2 is the same as square root of 2 times square root of 13. So it's 2 times the square root of 2 times square root of 13. We'll cross that bridge in a little bit. Square root of 2 squared is 2. Two and 13 is 15. A product of roots, the product of roots is the root of the product. 2 times 13 is 26. Can't really break it down any further. They want radicals, guys. They want radicals. They don't want an exact answer unless they ask you for an exact answer. Most of the square roots aren't going to give you the quote-unquote exact answer. They're going to give you an irrational number that goes on forever. They don't like to do that until it's necessary to do that. That's frequently what goes on in math. Now, if they want an answer at the end of the day, an approximate answer in a chemistry problem, a physics problem, engineering problem, you got to go a little further than that. Then obviously you got to do that. They're looking for an answer there, rounded to the nearest 3 decimal places, rounded to the nearest. Well, there you got to go. You got to go with it. You got to give me this guy. The square root of 26 is 5 point something, going on forever. Double it. Double the 5 point something. Double it. Add 15 and divide that sum. At the end of all that by 11. That's some of the stuff they're talking about there. I've already done a good amount of stuff, guys, on this stuff. I'll try to try to reasonably talk about some of this stuff. I think we already have talked about it. We were like solving some of these problems anyway. So let's see what we can say about it. Sometimes they might have the right answers in here. They may not. But let's see what we do here. Let's do 11 and 13 and then kind of jump around a little bit from there. All right, guys. See what I can say. Exactly where I want to go with this thing. Number 11. Now they want something like this. Again, it's a little bit of a jigsaw puzzle how this stuff, and it's nobody's fault. I mean, there's just so many ways to write There's so many ways to write the answers here, you guys. So, I mean, that's where it gets a little tough sometimes. Yeah, here they want an actual, here they're going to keep radicals for, let me just see here, guys. Let me look at it. For 10 and 11, they want it in terms of radicals, you guys. Now, how do you know that? They didn't do radicals in the past. They did exponents, right? I'll try to make it really clear to you guys what I'm going to do, or at least exercise some kind of flexibility on something like that if there's not clarity. But usually, for those of you guys taking the math class with me, you know, it should be pretty clear how they're asking us to do certain things. Okay. Let's again with that in mind. I might do both of these actually. Let's do 10 and 11. I think it might be worthwhile. And they want it in terms of radicals. I think the way they had done it last time. Let me just see exactly what they had done. Right, okay, so they should look a lot alike, guys. I don't really need to do both of those, but let's try to err on the side of caution. I got a little bit of time here, maybe I can pull it off. For 10, they got 5 equals this. I'm sorry, for 10 they got 5 over the cube root of 9x squared. They want that. You don't want exponent. Here they want it in terms of radicals, somehow simplified. Well, this, you really got to watch it. You got to really figure out what you're going to do here. I'll tell you what I'm going to do. The cube root of this is 9x squared to the 1/3, which is equal to, bring the 1/3 in there, 9 to the 1/3 power, that's the cube root of 9. It's going to be 2 something. And the cube root of x squared, which is x to the 2/3. So you're looking at this. You're looking at this. Now what? Well, they don't like radicals in the denominator. I'll tell you what I'm going to do. Let me try to non-radicalize this thing by multiplying by a special 1. That'll put 2/3 on the 1/3 to give you 3/3. And a 1/3 onto the 2/3 giving you 3/3. And let's make that go here. This is where working with exponents is a lot more convenient than working with radicals. And then you can make it into radicals at the end of the day. Then you can make it with radicals at the end of the day on this thing. So you look at this thing and let's just see where it's going to go. I mean, let's just try to see where it's going to go, I guess you could say. Let me multiply across. It's going to be 5 times 9 to the 2/3. I need to cross that bridge somewhere. And then I got this. 9 to the 2/3 times 9 to the 1/3. 1/3 and 2/3 is 3/3. You engineered that to happen. X to the 2/3 times x to the 1/3, that's x to the 3/3. Interesting. 3 over 3 is 1. 9 to the 1 is 9. 3 over 3 is 1. X to the 1 is x. See what we can do. We got a 5 right here. What do you say? You take 9 squared, you take an x to the 1, you take everybody to the 1/3. Is that true? If you take the 1/3 in there, you get 9 to the 1/3, you get x to the 1/3. Yeah, sure. If I exponentiate to the 1/3 power, I get 9. If I exponentiate If I exponentiate to the 1/3 power, I get 9 to the 2/3, and I got x to the 1/3. That's interesting. Let's see. Gee, how do you want to go on this one, guys? I mean, let's see how you want to do it. I tell you what I'm going to do. I'm going to take the whole thing to the 1/3 power means the cube root. 9 squared is 81. X is x. And 9x is 9x. It looks like I'm almost done. Yeah, it's more to it than meets the eye. You got a 5 right here. Didn't we say the root of the product is the product of the individual roots? Be careful. Don't get careless. Don't put square root there when it's cube root. Don't get careless. Let's take a little snapshot of what's going on here, guys. Is it true that the cube root of 81 is the cube root of the product 27 times 3? Is 27 times 3 81? 27 times 3 is 81. Why did I do that? Because 3 times 3 times 3 is 27. It's a perfect cube, 27 is. Kind of gets me out of the woods a little bit. All right. The cube root of 27 is 3. The cube root of 3 is whatever it is. It's a messy number, but there it is. The cube root of 27 is 3, though. And that's pretty good. Because this right here is 5 times 3 cube root of 3 times the cube root of x no easy way to write this one, but I just ran out of room, guys. We got it right here. I'll write it again. And I got the 9x right here. Got the 9x right here. The 3 and the 9 cancel. You got 5 times the cube root. Get the 5 far away from there. You know, at least so they know it's, you know, there's a differentiation of what's going on here. The rule is they don't like radicals in the denominator. And the less radicals that you have, the better. So the product of two radicals is the radical of the product. So the preferences get to here. And there's your answer. So it's a pretty fascinating argument. If you want to do things in the strictest sense, there it is. I mean, there's a lot you can do if the radicals are more convoluted, more complicated in one way or another. There's a lot that can be done. They're not really going down that road. They let us off the hook a little bit. Theoretically, we could go down that road. I'm confident you guys could pull it off if it came to it. They're not really asking that too much. So, so that's kind of what's going on in that regard, guys. All right, that's what we got. There's your final answer on that one. For number 10, number 11 would proceed in a very similar manner. You know, So we got that right there, you guys. Let's leave this, I think. I don't know, we can leave it, we can not leave it. You've got all the, I think we got all the tools to do it. Let me write just on this one and erase the whole thing. I need to erase the whole thing. Let me write number 11 right here. Let's kind of like whip through it, I think in a pretty decent manner and see what's going on. All the way down to here. Let me see if I can do that. So that's 10. All right. What's 11 all about? 11 is the same argument as the other one, guys, but I just think it's worthwhile. I mean, what if they played it like this? Well, they still got a 5 up there. Instead of a 5, they got a 49 x squared, still a cube root. So, okay, that's all they went. I like the way they constructed this thing. How'd you do it? How are we going to do it? Just follow the blueprint that we got up here, I guess, if anything. 5 on top. This whole thing to the 1/3 is 49. (49x squared), the quantity 49x squared to the 1/3 power. Now what? Look at it. What we got is 49 to the 1/3. And we got, you're just bringing the 1/3 in there. You're exponentiated quantities. If you're exponentiating an exponentiated quantity, when you exponentiate an exponentiated quantity, you multiply the exponents. When you exponentiate an exponentiated quantity, you multiply the exponents. You are exponentiating an exponentiated quantity in a sense. So you'll multiply the exponents to actually do that. So as long as there's a product, you can go here. This is to the 2/3. Okay. Now what? You're trying to get it to not be to the 1/3, to not be the 2/3. You want it to be to the 3/3, to the 3/3. The special one what do you got? Well, okay, you kind of constructed it that way. You're going to have on the tops, you're going to have this. On the bottom, you got this guy going to here. It's going to be 49 to the 3/2. You got this guy going to here. It's going to be x. I'm sorry, you're going to have 49 to the 3/3 rather. And here you're going to have 2/3 and 1/3, x to the 3/3. So that's not a bad way to go. There's a lot that can be said here. Let me try to see exactly what I want to say on this one. How we actually want to go with this. I guess they kind of made the jump a little bit on this one, so let's us make the jump too. You got 49 squared. You got x to the 1, or just x, and the whole thing is going to be to the 1/3. You're kind of like, how to, if you exponentiate an exponentiated quantity, you're multiplying exponents. If you take something out of the exponents, you can do it and take it and make it an exponent on the outside of a quantity. You do a whole lot of math here, and we've done a good amount of math to do it. So let's see what we do have. I mean, what we have is, at the end of this, 49 to the 3/3 is 49 to the 1. X to the 3/3 is x to the 1. What's going on here? Some pretty big numbers here. I don't know if I want to square 49. If I square, there's a mathematical trick to that. If I were to square 49, it'd be 2401. You actually square 49, you're going to get 2,401. Is that true? Let me argue that one. Let me look at it to be sure I know what I'm talking about here. You're going to bring it down by 100. You bring it down by 99, guys. 2401, you guys. If you actually square this, you'll get 2,401. I think I got a better idea. I got a little bit better idea. At least now that the numbers are big. I don't have to do too much gymnastics. Are you guys okay with 49? Let's kind of play it. This whole thing to the 1/2, to the 1/3 rather. This whole thing to the 1/3 is this. 49 squared is 7 times 7. Isn't 7 times 7 49? 49 squared is the quantity 7 times 7 squared. The quantity 7 times 7 squared is 7 times 7 times 7 times 7. 7 to the 4th. Isn't 7 to the 4th the same as 7 to the 3rd times 7? That's what 49 squared is. This guy's x right here, and you're going to see what I'm about to do in like an instant. We got to talk. This is what it is. This is what it is. Tell me how you feel about it. The root of a product is the product of the individual roots. I purposely constructed this. Five is 5. What's the cube root of 7 to the 3rd? How about 7? What's the cube root of 7x? Well, whatever it is, I ain't going to be able to do too much with that. Here I got 49, x on the bottom. And the 7's canceled. I got 5. Got 5 times the cube root of 7 times x. Over 7x. Looks a whole lot like what I did over here with problem 10 from old practice exam number 3. Still staying with old practice exam number 3, this would be 11 on that. It's a good problem. It's forcing you to do a lot of mathematics. Those of you in chemistry, physics, engineering, whatever, look at this and say, well, when am I going to need that? Well, maybe not this convoluted, but again, knowing how radicals operate, being able to manipulate with the laws of roots, with the laws of exponents, it's immensely important. Very, very useful. Really opens doors for you, you guys, when you do this stuff. So it's coming out to something like this when you do it, okay? So okay, so on and so forth with stuff like that, guys. Again, now they go into a problem like number 13 from old practice exam number 3. How do you actually solve a problem like that? Problem number 13. You do it remembering that you do not simplify addition or subtraction unless you have like terms. If you don't have like terms, you're not simplifying. You can still add them, but you're not simplifying. It's a big thing. So, okay, guys. Okay. See how 13 plays out. Is saying, what if they get, now this might look a little easy, this compared to some of the stuff we've already done, you guys, probably not going to be that hard. Probably not going to be too difficult. Just got to be careful. All of it's underneath the radical. Here, the 6 out in front of it. You got 125 right here. Next to the third. The whole thing's underneath the radical. Be very particular, be very specific how you answer questions. Make sure that you're communicating to another person to the best of your ability. I'm not some authority on this. I think I can do this better than I did 20 years ago, certainly better than I did 30 years ago. Still doesn't mean I do it great or anything, but make sure you're very clear in your communication. It's a very important thing, no matter what you're doing. Whether you're teaching, whether you're directing people in some regard, or managing people, or any sort of communication that's going to be worthwhile, from the medical profession, from the engineering profession, from you name it. The communication has to be very strong, very specific. You gotta want to look at things in such a way that there's no ambiguity. There's no ambiguity here, hopefully, because I wrote it big and I made the radical underneath it. I made the radical over everything. We know that the root of a product is the product of the root. So I don't know, you can write this a whole bunch of ways. Is it true? I can write this, the root of 80, this is square root. Here's a 6 right here. It's the root of this guy, the root of this guy. Already the tail end, they agree. So there's going to be a lot of agreement here, which means I can simplify the addition or subtraction that I'm asked to do. Tell you what I'm going to do. I got to get an easy square root. They do not want, usually, on the math aspect of things, guys, they prefer things in radicals. And if they ask you for an answer rounded to a particular place, that's when you do that. With the physics and the chemistry, they tend to get away from that a little bit. They want an answer. The answer is probably, if it involves radicals, not going to be exact. But they'll say, give me 2 decimals accuracy. Give me accuracy to 4 decimal places, or whatever they're going to tell you. We'll deal with that on that aspect. But for the mathematics, typically they want things that remain in radicals. Tell you what I'm going to do. There's a lot of ways I can write 80. 1 times 80 is 80. 2 times 40 is 80. 4 times 20 is 80. 5 times 16 is 80. And maybe that's something to look at, because the square root of 16 is 4. So 16 times 5 is 80. Is it true that x cubed is x squared times x to the 1? 1 and 2 is 3. Sounds good to me. Is it true that 125 is 25 times 5? Is it true that x cubed is x squared times x? Is it true that the product of roots, forgive me, is it true that the root of the product is the product of roots? The root of the product is the product of roots. X to the 1 is just x. Is it true that the root of the product is the product of roots? Is it true that the root of the product is the product of roots? So, looking pretty good. I mean, so we're doing all right. So, look what I'm doing, guys. Look what I'm doing. The square root of 16 is 4. Square root of 5 is the square root of 5. The square root of x squared is x, and the square root of x is the square root of x. We're going to talk about all of that in a little bit. The square root of 25 is 5. The square root of 5 is the square root of 5. For our purposes, we don't mess with it. The square root of x squared is x, and the square root of x is x. Let's put things together a little bit, guys. Let me put the 4 times the x, and let me put the square root of 5 times the square root of x. Let me put, let's do a bunch of things here, I guess. That's where we want to go here. What's 6 times 5? It's 30. Let me put the x right next to it. 6 times 5 times x is 30x. They want as few radicals as possible. Whenever possible, they don't want division by a radical, and they don't want too many radicals there. So they want you to unite all the radicals. So you got this right here. The square root of, the product of square roots is the square root of the product. They want as few, again, I just told you, they want as few radicals as possible. The product of these two roots is the root of the product. Okay, look, whatever mess that is, and whatever mess that is, they're the same mess. The x's are the same too, I guess you could say. If you put an x here, x times this mess, and x times that mess. All the letters and symbolism and everything, all of it corresponds. The front ends don't. 4 boxes minus 30 of the same kind of boxes means you're in the hole. 4 minus 30 is negative 26 of those boxes. And that's what they're trying to do here. And that's what they're trying to do there. All right, you guys? So on and so forth. I mean, these games got played a little bit. I think I already, we play the games enough. I guess we got a decent feel for what the heck's going on. Problem like number 18. I can do, it's arguable. I think we've got enough of the background on it. Maybe we need to do it, maybe not. Just do it for the heck of it, kind of feel what's happening. Actually, we don't. I mean, that's just the difference of 2 squares. You multiply it out the way I've shown you in the past. This stuff should be pretty decent. Done some other stuff with the I. Remember, I is the square root of -1. We've done a whole bunch of stuff that way. Let's see what we can do here. Let's look at like problems. It's hard to kind of call it what works, what doesn't. We did a whole lot of problems, you guys, with the quadratic formula. We had a whole lot of problems with the quadratic formula and solving quadratic equations with or without the quadratic formula, completing the square, things like that. We've already done that, so that's okay too. That gets us, we're kind of out of the woods that way. Did some great word problems as well. I think we're doing great. We're in decent shape here, guys. Do some of this stuff. Let me do 33, 35, 36. Old practice exam, old number 3, when we do that thing. Still staying with old number 3 on this one, guys. All of this is old number 3. What we have here if g of x is equal to this, find g0, find g41. G0, you guys, in for x, is simply 2 times 0 minus -1. 2 times 0 is 0, minus 1 is -1. The square root of -1 is I. I don't know how hopefully they didn't say, undefined on that one or something like that. I think it's hard to know how you want to play this and how people are giving the answers sometimes. This is fine. In my book, this is absolutely fine. Yeah, there's I for this one. And if you want to put, for this one, 41, G at 41, two times 41 is 82. 82 minus 1, the square root of 81 is 9. That's where they're going right there. Let me go for 35 and 36. These are 2 word problems. We already did a lot of word problems, or at least some strong word problems at the very least. 35 and 36. Let's see how we're going to go there. Let me try to speed this thing up a little bit and find out where we want to go. All right, guys. See what else we can say here. We got 35 and 36. 35, police use the formula S equals the square root of the product 30 FD to estimate the speed S of a car in miles per hour, where D is the distance in feet that the car skidded, and F is the coefficient of friction. If the coefficient of friction on a certain dry road is 0.89, and a car was traveling on it at a rate of 60 miles per hour, how far will the car skid round to the nearest foot? There's a lot here. I guess this is a pretty decent physics problem as well, if you want to talk about it that way. The way they made this, as far as a math problem is concerned, they made it very, how do we say it? I mean, they made it very convenient. All the stuff's gonna like spit out okay, and you don't have to worry about the units. I guess they're talking about this whole process, the coefficient of friction. Guys in physics were using mu, the Greek letter mu, lowercase letter mu. Here they're just using F. It's more or less a scalar quantity for our purposes. And in addition to that, they're saying miles per hour in feet, and they've got the formulation set up in such a manner that if you plug in miles per hour, if you plug in feet, and if you plug in the coefficient of kinetic friction, or whatever friction, F, whatever for our purposes, if you plug it all in, the F, miles, and then you got miles per hour somewhere else, you got feet somewhere else, it all works out. They made it so it all works out. So, if that's the case, police use this formula to estimate the speed S of a car in miles per hour, where D is the distance in feet that the car skidded, and F is the coefficient of friction. If the coefficient of friction on a certain dry road is this, and a car was traveling on it at a rate of 60 miles per hour, how far will the car skid round to the nearest foot? Like I said. Now, again, these are old practice exams. Overwhelming majority of the answers they're given at the back are right, so that's not a big deal. On occasion, people make mistakes. I make them, other people do as well, so kind of be aware of that. But again, know the basics of what's being taught here, and if it came down to it, can I do this on my own and actually find out what's going on? Can I catch somebody in a mistake? Sure you can. If you know what you're doing, you can correct your own mistakes, and you can correct other people's mistakes as well. Majority of the time, I'd like to think we're all doing this correctly when we're doing it. On occasion, we're human. We're always human, and on occasion, we make mistakes. Okay? Talking about this a bit, they're saying this. They're saying for 35 on this one. Old number 3. 35, they're saying S is the square root of the product 30 FD. Basically, guys, if there's a big skid distance, all other things equal, then let me just see here really quickly here. D is the I'm sorry. If there's a big skid distance, the speed of the car had to be great. If all other things are equal, if all other things are the same day, same road, same time of day, same road conditions, F is the same at that particular moment, that particular time. If 2 cars are flying down there and they slam on the brakes, part of this experiment, there's nobody around, hopefully, right? They slam on the brakes. The car that is going to skid very far, if there's a very long skid, that's associated with a great speed that was being traveled. If car 1 skidded 4 times further than car 2, the square root of 4 is 2, its speed must have been twice as much. That's interesting. It's actually believable even. If you want to believe that, believe it. Why? Because if it's the same, say it's the same car too, same exact car, though even here you can, I don't even think it matters, the mass of the car. Within, that's something else we can explore, I guess, some other time. But there's a lot going on here. Well, it's more massive, it's going to go further. Yeah, but the brakes are better, let's say, or at least if you can bring them to a dead stop, there's more mass that's got to move as well. Okay, this is interesting. If one of them is D and the other one is 4D, if one of them is length, 1 meter, and the other one's length 4 meters, whatever. Let's call them, one's D and the one's 4D. One's 4 times longer. The square root of 4 is 2. Twice the speed. Why is that? Kinetic energy is 1/2 mass times velocity squared. If you square a velocity or magnitude velocity, kinetic energy is 1/2 mass. If you square a velocity or magnitude velocity that is twice as big as the magnitude of another velocity, if the speed of one of them is twice as much as the speed of the other, when you square 2, you get 4. If you got 4, there's 4 times more work it can do. Force times distance is work. 4 times the distance for a given force is 4 times the work. It's believable. If you went 4 times the distance, that happened with 4 times more work being done. Twice the velocity, when you square twice the velocity, it's by a factor of 4 times the kinetic energy. 4 times the kinetic energy means 4 times capability of doing work. 4 times more work will be done, associated with 4 times the distance. Don't want to get into this too much right now. For those of you guys in physics and engineering who want to get into that stuff, that's something to kind of look at. So it's believable. What they're saying right here is believable, which I hope is believable. Why bring something up if it's not believable, right? So they're saying here they want you to find distance, given all this. Do you understand if 2 things are equal? And those of you just in my algebra class, you don't need to know that. If you're going to go later on and take some chemistry, they might talk a little bit about kinetic energy. Physics for sure, it's good to know that. Good to know. Right now, just straight out algebra, you're not going to worry about it. We're going to go with the formula they gave us. For those of you taking something different, want to take something different, associate. It's good to have that association. Okay. If 2 things are equal, they remain equal if you square both sides. The square of something square rooted is just the something. I want to find distance. The distance of the skid. This is not the only way to do this. But I think the more you solve things symbolically, and then at the end of all that, do something. That's something. So the more that you solve things symbolically and then plug things in, I think you're in better shape when we do that. All right. What are they saying here? If the coefficient of friction on a certain dry road is F, it's 0.89, and the car's going 60 miles per hour, do what you got to do. D is D, 60 is 60, over 30, what do you got? Well, you got 60 times 60 divided by 30 divided by 0.89. Two times 60 is 120. So you got this. Whatever that's going to be. They actually worked it out. I'm tempted to go with my calculator on this one, guys, just to kind of make sure nothing crazy happens. I got 134.83 something. Let me see here. I got 134.83. They wanted it rounded to the nearest foot. They got 135. You got it. Roughly speaking, 134.83. It's still not the best thing. It probably goes on, to what degree that goes on. It's probably not an irrational number, but probably a number that does go on, repeats in some regard forever. The answer they got is 135 feet. But you're going that fast. It's roughly 135 feet to stop. Going that fast, roughly 135 feet to stop. Now here's what's important. Whether you're taking my physics class, whether you're taking any class anywhere, if you got mathematics involved, including geometry, algebra, a whole lot of stuff you can use, when you're doing this stuff. If the 30 is a constant, and it is, if the F is a constant for those particular conditions at that particular time, whatever, for those particular conditions, F is a constant, 30 is a constant. This guy calls the shots then. If the speed were doubled, now what's the ratio? It's the ratio of, V1 to V2. If this guy's speed is S and the other guy's, or let's take the ratio of the squares of the speed. V2 squared over V1 squared. If V1 is S, if V2 is 2S, I'm trying to write them. My 5's and S's look a lot alike, so I don't want to mess you up here. 2S, and this is just 1S. Speed 1, in scenario 1, the speed is S. In scenario 2, the speed is 2S. Compare the squares. You know that. I mean, if you're comparing the squares, you guys, you could the ratio of exponentiated quantities is the ratio of the quantities exponentiated. That don't mean a whole lot. What does that mean? It means if you got 2S right here, you're squaring it. You got S right here and you're squaring it. This is 4S squared. The other guy is just S squared. The ratio is 4 to 1. Is that the same as 2S over S, then square it? Yeah, they cancel, you got 4. Either way, you got 4 over 1. If you're comparing things that are being squared, if this guy wasn't going 60 miles per hour, he was going 60, and we did the whole song and dance. You saw me do the song and dance. We squared 60 and we divided it by the product of 30 times that. We saw 60. They told us 60, we squared it, we did the whole thing. What if the guy wasn't going 60? What if he was not going 60 miles per hour? He was going 120 miles per hour. Twice what 60 is. Didn't we say when you compare squares, if the ratio is 2 to 1, and you square it, you get 4 to 1. If it's 60, this is going to be 4 times the size of this. This is going to be roughly 540 feet, 4 times 135. More accurately, 4 times 134.81. Forget it. I'm not going to worry about that. I'm going to say it's 135. 135 feet to come to a stop if you put the brakes on, if you're going 60 miles per hour. If you're going double that speed, if you're going at 60 miles per hour, it took you about 135 feet to stop. If you're going double that speed and you put the brakes on, it's going to be, what's the ratio of 120 squared to 60 squared? It's the ratio of 120 to 60 and then square it. If you do that, there's 4 times the kinetic energy, 4 times the distance, 4 times the work will be done, which is 4 times the distance of the skid. If the skid is 135, that's 540 feet, 4 times the 135. Stop. If they wanted you to look at it that way. 35. 36. The maximum distance d in kilometers that you can see from a height h in meters is given by the formula d equals 3.5 to the square root of h. How high above the ground must you be to see 30 kilometers? Round the answer to the nearest tenth of a meter. Okay, so let's see what we can do about that. All right, guys. So see what we can say here in this one. They're saying should be pretty straightforward. This one should be a little easier. The maximum distance d in kilometers that you can see from a height h is given by the formula. Well, here's how far I can see. So let's see here, guys. This is, again, old 3. Okay, these markers are not good. Let's see if I can. Nah, it's not going to work, guys. Sorry. Hopefully this one writes. "36, they're saying d equals 3.5 3.5 times the square root of h. So let's see what we got here, guys. You got this right here. They're saying, essentially, guys, forgive me the repetition of this. The maximum distance d in kilometers that you can see from a height h in meters is given by that formula, 3.5 times the square root of h. How high above the ground must you be to see 30 kilometers? Again, round to the nearest tenth of a meter. Every 1 kilometer, you guys, is 1,000 meters. So they want this thing to the nearest meter. So we got to figure this out. Now, I don't know how they, it's a hard call. Hopefully they haven't done anything too, that's an interesting thing here. Now here, I think we need, okay, the maximum distance d in kilometers. The maximum distance d in kilometers that you can see from a height h in meters. Okay, they already got it figured out for us. This will be kilometers if you put this in meters, from height h in meters. So, how high above the ground must you be? Okay, let's figure this out. Let's square both sides. This right here is 12.25. Let me kind of kick that around a little bit, if you don't mind. Let me just see if I can actually believe that. Let me think here. 325. Yeah, 1225. Yeah, 12.25. Square this. You got h. Solve for h. This is not the only way to do this. You could plug in plug this in, so you're doing good that way. H is equal to this. Right, it's probably the best, that's probably the best way to do it. Go symbolically and then try to go for it at that point. They are saying D's got to be in kilometers, right? D's got to be in kilometers. It's 30 kilometers, and 12. It's going to be 30 kilometers squared. Then it's going to be this. It's going to be 900 divided by 12.25. 25, I got a way to do this, actually. I think there's just kind of a shortcut you can do on this. You could make 12.25 25 over 2. 900 divided by 25 over 2 is 900 times, what's 25 over, you're dividing, 12.25 is 25 over 2. Dividing by 25 over 2 is the same as multiplying by 2 over 25. 2 over 25 times 900 is 1800 divided by 25. 1800 divided by 25 is 72. Let me just make sure that's true. 1800 divided by 25, 25 goes into 104 times 18, should be 72 meters. I think we're okay. Let's have a look at it, see how they actually solved it. I do not see how they got 73.5. I do not see it. Let me see. I could be making a mistake here. In fact, I am making a mistake. Doesn't work that way. If that would have been 12.5, 72 would be the answer. If it was 12.5. It's actually 12.25. So yeah, it's not the answer. It's gonna be a bigger answer. That's my fault. If it's any meritorious, I guess, if it was 12.5, what I just said is true. It's not 12.5, so it doesn't matter what I say. It's not the right answer. So what do you do on that one? They're saying it's 73.5 on that. I think it's about right. Let me confirm it. Though I don't think they made a mistake on that one. I think it's on the mark. I think it's spot on that one. And there's ways you can do this in your head as well. Let me not burden you with that. It would actually be, the way the whole thing plays out is it would be 12 and 1/4, which is the same as 49/4. Flip it around, it'd be 3,600 divided by 49. That's 73.469. 73.469, about 73.5, roughly 73.5. Doesn't matter. I mean, on that one, guys, there's a lot of ways you can play it, but it's roughly equal to, and I think they're asking the question to the nearest tenth of a meter. That's going to round off to 73.5. Looking good. So 73.5 meters on that one. So a lot of ways to look at this stuff, guys. I think if you can get things, if you can take as much of the non-numeric symbolism as far as possible, I think you're giving yourself the most insight. If you do things strictly non-numeric symbolically for as long as you can, and then plug in the appropriate values to get any sort of approximated answer that they would want. I think it's a great idea. Go along those lines. All right. So that's some of what they're talking about there, you guys. So there's a whole bunch of other stuff that I already did, so we don't need to do it again. Did other word problems as well, and then we talked about how things move around, and we talked about the parabola, the ellipse, and the hyperbola. Forgive me, we talked more than that actually. We talked about circles, ellipses, parabolas, and hyperbolas. Circles, ellipses, parabolas, and hyperbolas. And we talked about some of the formulation of that, especially with circles, ellipses, and hyperbolas. I gave you the formulas for that and the asymptotic equations of lines that bound the hyperbola in one instance, okay? They talk about some other stuff as well, you guys, that I think is worthwhile for us to know. They gave a couple equations, so you're doing a function of a function in some cases, and how you find inverse functions and stuff like that. And I already showed you how to find inverse functions. There's some interesting, I guess you could say some interesting formulas here for actually doing some things and getting some answers here. So let me go to those a little bit, and then go into logarithms and exponents and stuff like that, and how this stuff plays out. But I think you got the lion's share of what you need when we're doing this stuff, okay? And I guess we follow the formulas and we should get it there. Again, not always, well, you've seen me already. I almost gave you the wrong answer here until I caught myself, right? Or until I was caught when I actually looked at the answers. But sometimes the answers aren't going to be right, you guys. You got to look. You got to be able to catch yourself and or somebody else. Again, the majority of the time, You like to think you're doing the right thing, and you are. The majority of the time, you're going to get this stuff right. But always be checking your answers. Always check on what you're doing. That's for sure. What else we can say? All right, guys. Let's see some stuff we can say. Let's see how we feel about some of this stuff. Let me see if I can get more stuff out of here if I need it. I get it right here, so I should be okay. They talk about a couple things and what you want to kind of look at. There's some shorthand. They say, like, for example, f plus g of x. That's just shorthand for saying f of x plus g of x to get, like, you're actually getting, that's your new function, so to speak. You could say f minus g of x, and you can get f of x minus g of x. You can go f times g like that, fg like that. No dot, no anything. So sometimes they put a little dot here or something to do this. Fg of x means f of x, get an answer, and then g of x, get an answer, and then after that you multiply the two. They say f over g of x. That means f of x divided by g of x. There is the limitation, ladies and gentlemen, that you don't want. There is the limitation. You don't want you don't want g of x. You don't want the number on the bottom to be equal to 0. You cannot have division by 0. They got this other one that looks a little bit like fg, but it's not. It's f composition. It's almost like it says fog. A circle here. F composition g of x is f of the g function. What does that mean? Well, work from the inside out. Start at x right here to the right of my hand, to the right of the white paper. Start at x and do the g function on it. Once you get whatever the g function is, do the f function on to the g function. That's called the composition function. So they get into that a little bit. So what are we talking about? Some stuff is easier than others. I mean, they talk, again, this is all, old, from old number 3. But, I said the old practice has all this stuff in there as well. So you can't, why replicate the stuff? Why duplicate it? Okay? Let's see what we can do, guys. If you had f of x is equal to x plus 8, and you got g of x equals 7x plus 2. X is 1x. F composition G is this, atom. If you add this, that's F, and you add this, that's all you're doing. What are you doing? You're doing what's up here. I don't need to rewrite it again, guys. You got this, you got this. You get these glasses off. You can't see what I'm doing from a distance. This, and that. So you know that. We all know that. We got that right there, and that's what we're working with. So we got something like this, guys. You do this. We got 8x plus 10. When you actually do that. So on and so forth, guys. They play the game pretty much here on that. If you were subtracting, they had something else going on. They had if you had this is problem 67. Just kind of give you some numeric bearings here on this. Old exam number 3. Old number 3, number 66 right there. 68 is saying fx (9x minus 8) gx equals 3x minus 9. And they're going to play the game again. This time they're going to say, do this one. Well, I already showed you what that means. That's the second one. Second one down. The 66 was the first one up there. 68 is the second one down from there. There's one down from there, second one there. You're doing this right here. You're just simply subtracting the two. So you're going minus 3x minus 9. 9x minus 3x is 6x. Negative 8 minus a minus 9 is plus 9. That's plus 1. Let's make sure it's right. I mean, unless I wrote something wrong here. But basically, this is plus a negative 8. This is plus a negative 3x. And this is plus 9. Minus a minus is plus. Plus 9 and negative 8 is 1. 9x minus 3x is 6x. Okay, so you got what you got, guys. That's 68. Problem 69 is saying fx (3x minus 6) g of x equals 3x minus 6, 2x plus 6. You got this. They're asking for this now. How are you going to do that one? Well, pretty basic how you can do that one. You're going to go 3x minus 6. 2x plus 6. How that's going to play out. I mean, that's its own interesting dynamic in its own right. I don't know. I think a lot of, depends how I'm going to be teaching this class, you guys. There's a lot I got to know. They're going to talk to me, as I'm writing this, in about a week, I'm going to know more of what they're wanting. I know this stuff's going to help you, and I know nobody's going to have a problem with the fact that this stuff's going to help you. For those of you at MATC in my algebra class. UWM, I already know what I'm doing. So it's a little different dynamic if I've done it a bunch of times. With these new circumstances here, guys, for the MATC people, I think we're going to be fine. Well, this right here is good. It's going to help you out, and I know nobody's going to have a problem with you being helped out. Okay? Nobody's going to have a problem with that. With that in mind, I don't know. I'd probably leave it here. If you want to walk it all the way through and find out what the heck it is, a lot of ways you could play it, I guess. 3x times 2x. 3x times 2x 3x times 2x is 6x squared. 18x and negative 12x is positive 6x, right? Positive 6x, and here's negative 36, plus a negative 36. You know, when the numbers get really, really crazy, you may, I mean, I don't know, if this was like some polynomial that had 10 terms to it, this is a polynomial that had 20 terms to it, and the powers were like to the 20th power on down in one of them, and to the 30th power on down with the other, with yet the other one. You could probably just leave it as is. Here, it's not that hard to multiply the stuff up and get the answer there. So on and so forth, guys. They're playing the whole game that way. For something like number 70, again, this is old practice exam 3. For number 70, they're asking f over g of x f over g of x, and they're saying f, you know, f is, they said f was the square root of x, g of x was 2x minus 5. That ends the story. You cannot have x equal to 2.5. 2 times 2.5 is 5. 2x minus 5. If x is 2.5, if x is 2.5, 2 times 2.5 is 5. 5 minus 5 is 0. Can't have division by 0. But there you go. There's your answer on that one too, for that particular type of problem. 70. Well, they want to say the function of a function. So for this one right here, you guys, let's do something like, let's do problem number 71 and kind of give you an idea. They're saying the function of a function, that's the composition function. That's this guy. Let's stay with old number 3 as we do this. Okay. A number of ways you can maybe look at this and see what's going on. For this particular problem I want to do here. So what, I think it was 70 we're talking about. F of x, forgive me, 71 rather. how would you do this? F composition G of X is F of G of X. What does that mean? It's F of the G function. The G function, G of X, is X plus 2. You will do the F function onto this. The F function onto this is you treat this like it's X when you put it in the argument. So whatever you put, you will treat X plus 2 as the new X. So plug it in there. It's X plus 2 is going to behave like X. You got this. So that's it. I mean, you could, you know, there's a lot of ways to go here. F composition G depends what people are looking to do, I guess. You can write it like, I would personally leave it like this. I wouldn't have a problem with it unless they ask us otherwise. But I think we're fine. You can write it like this. And then here, you know, that ends the story there. And then you can plug in. They want you to evaluate that. They want you to evaluate that at 2. So F composition G at 2 means X is equal to 2. Put a 2 right here. Put a 2 right here, add 2. 2 and 2 is 4. Square it. Put a 2 right here, add 2. That's 4. 2 plus 2 is 4. 4 squared is 16. 2 and 2 is 4 times 6 is 24. 24 and 16. Okay, let's just look at it one more time. I think we're fine. But at X equals 2, put a 2 right here. 2 and 2 is 4. Square the 4, and you get 16. 2 and 2 is 4. 4 times 6 is 24. 24 and 16 is 40. You're done. To write like this. Like I said, if it gets complicated enough, guys, if they ask you, hey, well, yeah, I'll take it. I don't think anybody's going to nickel and dime you right here. I'm not. We got enough going on. My goal is that you know a lot of this stuff, guys. I'm not going to get petty with people. Something like that. We'll see what they're asking you. Now, to say, please take this further, evaluate it further, yeah, you got to do it. If there's some explicit thinking. Within this context, you're probably okay. What is this, for the record? Square that. The quantity x plus 2 times the quantity x plus 2 is x squared plus 4x plus 4. This is 6 times x is 6x. This is 6 times 2 is 12. 6x and 12, keep that in your mind. What's x squared? You know, what's x squared plus 4x plus 4 plus 6x plus 12? You know, F composition G of X, it's x squared. 4x and 6x is 10x. 4 and 12 is 16. That'll work. That'll work. Okay, we got it to here. Okay, that's 71. There is some other stuff they do, and based on some of the formulations that we've done in the past, how to actually do some stuff. Again, you run out of time a little bit, guys, on some of this stuff. I'm not going to be able to do all of it, but I think I've given you the lion's share of what you do need to know when you do some of this stuff. There's a good amount of stuff here. So let's see here. Let's go over to logarithms a little bit and remember some stuff that we won't do vis-a-vis that. All right, guys, let me write some stuff down pertaining to logarithms. All right, guys. Remember a bunch of stuff. I mean, we remember that for logarithms, if you start with x and you exponentiate, and then you get the logarithm, base b of x, you get back down to x. If you start with x and then get the logarithm, base b of x, and then you exponentiate that, you still get x. And you saw me do that if we were doing with anything we had. If you do the logarithm, then exponentiate appropriately, you get back to x. If you exponentiate first and then get the logarithm appropriately, you still get back to x. You do one then the other, you get back to where you started. They're inverse functions of one another. You know, we did say that there was a lot of do's and don'ts here. The logarithm of a product is the sum of the individual logarithms, regardless of what the base of the logarithm is. The logarithm of a quotient is the difference between the individual logarithms, regardless of what the base is. The logarithm of something exponentiated is the exponent times the logarithm, regardless of what the base is. And there's a lot of do's and don'ts. Well, these are all do's, and I told you a lot of don'ts. So you look at that, and I guess it's going to help us look at some of the stuff that's going on here. And exactly how far they want to take it, that's interesting in its own right. But we said a lot of other stuff too. Did we say that the way we were trying to find some of the stuff here, guys, there's some pretty interesting problems actually. This is still old number 3. Number 3, old. Okay, let's see what we got here. For old number 3, how the stuff all works out. We also said that there is, remember how we derived that last time? We said the logarithm base A, let's say, logarithm base A of some number x is the logarithm base B of x over the logarithm base B of A. Rather interesting how that plays out. The reason, trying to actually figure this thing out now, if you were to kind of confirm it here, guys, I don't want to get too crazy with the whole process here. If you multiply by the logarithm of A base B on each side, you got, I'm just going to confirm something really quickly here. Multiply on each side. if you try to just figure this thing out a little bit. If you put everybody, let me just kind of argue this a little bit with myself here, guys. I'll confirm this fact that we did it last time in the notes, you guys. I can't go back on the film right now, so I gotta see if I'm doing this okay on the cold way to do this. What you can say is this: it comes out to the logarithm base b of a to this power, because it comes out log base a of x right there. And we're making the claim that's the same as this. If you exponentiate both sides, put both of these, put this whole quantity on top of b as an exponent, put this whole quantity on top of b as an exponent, you end up getting a log a of x. Put this on top, if I put this guy on, if I put all of this on top of b as an exponent, then you just got this left over. If I put all this on top of b as an exponent, I got that left over. We're making that claim. The logarithm of x base a, the exponent of x base a, put as an exponent on top of a, the logarithm of x, the exponent of x base a, put on top the exponent of x base a, put on top of a, the exponent of x base a, put as an exponent on top of a will give you x. X equals x. Yeah, it's right. This is true. I used capital A last time, guys. Here I'm going to use x. I just think it's a little more, perhaps a little more straightforward in doing some of these. So this is some stuff you got to look at as we're still dealing with from old 3. From old 3 right there, guys. Okay, from old 3 right here. If you take the logarithm and then exponentiate, you get back to where you started. If you exponentiate first and then take the logarithm, you also get back to where you started. Here are some laws of exponents, and here's if you change a base. Okay, so you have that at your disposal. We found out it works out okay. It is a fascinating endeavor. How did you make this multiplication into a straight up exponentiation from this guy? If there's a multiplication of two things, you can take, well, you gotta be careful if they're both logarithms here, but if there's a multiplication going on, you can take this multiplication, the multiplication going on, you can take this item and put it up here as an exponent, and that's how it works. So what I did right here is, I took this guy and put it on top of him as an exponent, because if I do the logarithm, so basically log b, and this is the same log b, the logarithm of a times the logarithm of x, you could take this guy right here and come inside and put him on top of a, and get the logarithm of something exponentiated is the logarithm of the something times the exponent. And this guy's the exponent. This guy and this guy are the same thing. It's the exponent. I hope that makes a little bit of sense. It is an exploitation of the reality of this third principle that you can actually confirm that this is indeed true right here, you guys. That this right here is indeed true. Okay. That we can look at. Okay, so we got 1, 2, 3. Let me number them as such. This is 1, this is 2, this is 3. When I'm going through it, maybe it'll kind of help things out a little bit. Okay, that's just a confirmation. All right, they ask a bunch of ways to write this stuff. Let's look at 84 and 86, the old stuff. From the old number 3. 84, write the expression as the sum or difference of logarithms. Break it down as much as you can. Logarithm base 3 of 3x over y to the 5th. 3x over y to the 5th. So, let's have a look here. Let's just make sure I wrote it down right. Yeah. So the logarithm of a quotient is the difference between the logarithms. The logarithm of a product, 3 and x, is that, and the logarithm of something exponentiated is the exponent in front. 3 is the same as 3 to the 1. What is the exponent, base 3 of 3 having 1 as an exponent? It's going to be 1. So we got that. See how they wrote that, guys. I want to make sure that we're all in agreement with each other here on this stuff. Yeah, they blew it. No big deal. I blow it all the time, but that's a better way to write this. The logarithm of 3 base 3 is 1, period. That ends the story. So that's going to happen. You saw me blow it a few times. It's going to happen. We're going to do it sometimes. So this is the right way to go. Take it further. What did we just do? Let's do it one more time. The logarithm of a quotient is the difference between the two logarithms. The logarithm of a product is the sum of two logarithms. That's this. The logarithm of something exponentiated is the exponent times the logarithm. I'm using 1, 2, 3 here, guys. Using 1 in the first, I'm using 2 in the first instance, then number 1, then 3. So on and so forth, guys. That's how it's working out. They're trying to get slick here. It's kind of neat. They're talking about number 86. I think you'll find it of interest. Problem number 86, how that plays out, what they wrote there. Okay, let's talk about it. Again, guys, if you're doing 300 problems, you're going to make mistakes sometimes. It's not, overwhelming majority of what they did is great. I mean, these are great reviews. That's why I'm going to use them with you guys. The goal is to use them with you guys, okay? Because this is, people that put this together did a great job. All right, guys. Looking at this one, I mean, they're kind of a great look to it, I guess. Kind of a fascinating look at how they want to do it and what works, what doesn't here, I guess you could say. We've got the background. We can do it. 86 is saying if the logarithm, they're not telling you too much. They're telling you the logarithm base b. I don't know what base b is. It's some number. It's some real number. The logarithm base b, b is some real number. Don't know what it is. The logarithm base b of the number 3 is 0.61. And the logarithm base b, still don't know what b is, of the number, logarithm base b, the logarithm of 3 base b is, okay guys, let me make sure I'm doing this right. Which one did I choose? 86? Okay, let me not kind of, well, speaking of making mistakes, right? I'm about to make one here. Let's try it again. Number 86, the logarithm base b of 3 is 0.79 in this problem. The logarithm base b of 5 is 1.16. Fascinating. Find the value. What's the logarithm base b of 3 divided by 25? Pretty neat. It's not as hard as you think. It's not as difficult as you think. Use the rules. 1, 2, 3. Let's break them up. Let's see what's going on. Are you agreeing with me that the logarithm of a quotient the logarithm base b of a quotient is the difference between the logarithms, base b. May I call 25 squared? May I then proceed and say this? The logarithm base b of 3 minus the logarithm of something exponentiated is the exponent times the logarithm of the something. In plain English, you guys. That's it. What does that mean? It means this. They already told you what the log of 3 was. Base b. 0.79 minus 2 times log 5. This minus this. 0.79 minus 2.32. Right? It's like negative 1.47 at the end of the day on that. You actually do it. Let's see where it comes to. Okay, I wrote it wrong. I'm sorry. Yeah, this should be right. For some reason, I did it wrong. This is negative 2.32. 0.79 minus 2.32 is going to be negative 1.53, something like that. So let's see what they got here. There it is, yeah. In fact, it is, yeah. Negative 1.53. So at the end of the day, The answer is negative 1.5 86, negative 1.53. Yeah, sounds good to me. What it comes out to is this: 2 times 1.16. 2 times 1.16 is 2.32. 0.79 minus 2.32 is going to be not quite as far down as what I thought. It's going to be in terms of absolute value, it's going to be 0.21 more than 1.32, which is going to be 1.53. So it's a long story. Anyway, make a long story. I'm making this a bigger deal than I should. I mean, basically, it's this minus all that. You're going to get that for an answer, and you're done. So that's some of what's going on, you guys, as we're playing the game with this thing. Good stuff. I mean, pretty fascinating stuff. They're asking different things here. I'll kind of stay along the lines of what they're trying to do, I guess you could say, and go with this. But some other stuff. How do you do some of these problems? How do you work these problems? You got to have the dexterity, you guys. Work with the stuff that we've done. And obviously, as you're looking at this video, you've got a whole semester to get through this. You're reading the book. You're doing other things associated with what's given to us, but you got this resource as well, you guys. Know the basics, and man, you can get away with a whole lot. You can know a whole lot and really accomplish a whole lot with the mathematics that you want to get regarding what we're doing as far as the math class is concerned. For those people looking at this for a review of the mathematics, hopefully it's at least a decent review for you as well. You're going to need all of this algebra for a basic physics class. Oftentimes, no. You may need more in some other stuff, more of the trigonometry that I talked about a little bit, but maybe not as much, all of this stuff. But you know what? The more you know, you're going to need it at some point or another. This can never fail you if you've got a strong basis with it. I think it helps you out strongly. They say something like this. See, the thing is, calculators can't always, the calculators have logarithm base E, called ln, logarithmus naturalis, and logarithm base 10. They don't have logarithms to other bases, and that's why this right here becomes really useful in doing a lot of the stuff. This right here becomes very useful in doing a lot of the stuff when you do it. So you see it, you look at it, you say, okay, well, what does he mean? What I mean is, for a problem like number 88, the logarithm base 6 of the number 13, well, this ain't an easy one to look at. Well, I'll call him A. He's the one that's not easy to look at. X is 13, A is 6, X is 13, B is, I don't know, you can call it ln. You can use, I'll use log base 10. Log base 10 of 13 over the log base 10 of 6. You could just as easily have done this. I'll use logarithmus naturalis of 13 over logarithmus naturalis of 6. Still going to be the same answer. Believe it or not, still going to be the same answer when you're doing this. Absolutely, still going to be the same answer for the base that's going to be there. Fascinating. Fascinating stuff. Same answer either way. Just looking at it, do a little confirmation on it. If you get the logarithm of 13, base 10, you see your calculator's got base 10, and your calculator's got base e. It doesn't really have base 6, so you got to use one or the other. If you do that, guys, you grind it out. They got 1.4315. Same thing here. Promise. Now, unless there's a careless mistake, it happens sometimes, that should be it. You grind them out. Make sure you're not going, make sure that you're not going 13 divided by 6, get an answer, and then take log base 10. You get this logarithm separately. Get an answer. Get this logarithm separately. Then get this logarithm separately. When you're done, then you do the division. Get this logarithm separately. Then get this logarithm separately. Only then, get the result here, get the result there, only then do division. Do not go 13 divided by 6 and then get a logarithm. You're going to get it wrong. Okay? So 1.4315 for that one. Let's see what I can say here, guys. Give me a couple minutes. Absolutely, for that one, yeah. For how they're giving the answers here, guys. Solve the logarithmic equation. They got different ways to do this. They say what you do, how you undo it. How do you undo logarithms? You unite them, you make them into one big logarithm. Whenever in doubt, make everything into one big logarithm. And the way to undo a logarithm is to exponentiate each side. So let's knock out a couple of these and get a feeling for how this all proceeds. Okay, some of the other stuff I've already kind of done, so I'm not going to need to do it again, but if I finish this, I'm largely done with what I want to discuss regarding some of this stuff. Then there's some other stuff here as well. I've seen, and I want to just clarify a couple of things. I've seen some stuff done that maybe was a little premature on the part of the people like doing the original key on this thing. I want to kind of give you the difference here when you do some of this stuff. All right, there's a few things I want to say, and I think we'll be in pretty good shape to be done with it. Let me leave a lot of that up there. Let me just erase what I just put on there, and then we'll kind of take it from there. Um, 91, let's do a couple of these guys, see what we can do. 91, they're saying the log base 9, it's not written in the clearest fashion, but again, the typographical capability of doing something on some software back in the day wasn't always the greatest, and sometimes just not easy to do. Here's what it should write. Here's what it should say. The logarithm of x, base 9, is equal to negative 3. Solve it. Can I ask you something? If two things are equal, do they remain equal if you do the same thing on each side? If you have a square on each side, if two things are squared, you can square root each side. True. If two things are square rooted, well, I'll make it plain and simple. If there's a square somewhere, you can square root each side. If there's a square root somewhere, you can square each side. If you want to undo a square root, you square each side. If you want to undo a logarithm, you exponentiate on each side. What am I talking about? In plain English, guys. If this exponent right here, because that is what the logarithm is, it's an exponent, is equal to that exponent, that means if you put both of them on top of the same base, this is what I meant by this. If you want to undo a logarithm, please exponentiate and you get back to where you started. I got to get rid of the logarithm here for me to solve for x. I can't get rid of the logarithm by dividing by the word log. It'd be nice if I could. I'm not multiplying by 5 on each side, so that I'm not multiplying. If there's a 1/5, I'm not multiplying by 5 on each side to solve. If there's a 5, I'm not dividing by 5 on each side to solve. Here there's a log, and I can't go, oh, I'll divide by log on each side. I can't do that. I got to undo the logarithm. How do you undo the logarithm? I'm going to exponentiate on each side. What is the exponent of x, base 9, put as an exponent on top of 9? I said it gets you right back to x. If you take the logarithm of something and then exponentiate, ladies and gentlemen, you get back to where you started. If you take the logarithm of something and then you exponentiate that quantity, you get back to where you started. If I find the exponent of x and then put it as an exponent on top of b, I get x. If I exponentiate b and then get the logarithm base b, I get the number that was on top as an exponent. If you exponentiate, then get the logarithm, you get back to x. If you take the logarithm and then exponentiate, you still get back to x. Exponentiate, then take the logarithm, you're back to where you started. X in this case. Take x, exponentiate, then get the logarithm, you're back to x. Take x and get the logarithm instead, and then exponentiate, you're still back to x. That's what I've been trying to say here. I said this some time ago, I'm saying it again, that's the only way you're going to solve it. If there's a logarithm present, you're going to exponentiate each side. The exponentiation of the exponent of x, if you take the exponent of x, the logarithm of x, base 9, is the exponent of x, base 9. The exponent that'll give you x, when you put it as an exponent on top of 9, gives you x. Who's buried in Grant's tomb? 9 to the negative 3 is 1 over 9 to the positive 3. Nine times 9 times 9 is 729. You're done. It is the same argument. It is the same argument for problem 92. Same exact argument for problem 92. Here it is. They're saying log base 7 of the quantity 3x minus 14, the whole quantity, is equal to 2. Solve for x. Solve for x. Two things are equal. Two things are, there it is. If they're equal, they remain equal. If this equals this, they told us it does. If you put them both on top of 7, they're still equal. How do you undo a logarithm? Exponentiate it. If you find the exponent of the quantity 3x minus 14, if you find If you find the exponent of the quantity 3x minus 14 and put it as an exponent on top of, if you find the exponent of 3x minus 14 base 7, in other words, the exponent such that if you put it as an exponent on top of 7, if you find the exponent base 7 of 3x minus 14, you're finding the logarithm of 3x minus 14 base 7. The logarithm of 3x minus 14 base 7 is the exponent of the quantity 3x minus 14, such that if you put it on top of 7, you get 3x minus 14. Well, you just put it on top of 7. So you are getting 3x minus 14. You're undoing it. How do you undo a logarithm? How do you undo a logarithm? Please exponentiate. Do the same thing on each side, or it's not an equation anymore. Remember, they said these two were equal. I wrote them down. They were both equal. They tell us they're both equal. What's 7 to the 2? Well, there's no mystery on that one. You got that. At that point, why don't you add a positive 14 on each side? Okay? Add a positive 14 on each side. Guys, you're doing old-fashioned algebra right now. Pretty simple old-fashioned algebra right now. You're adding 14 on each side. Divide by 3. X is 21. It's that simple. Don't read too much into it. 94. There's a slick way to get out of this one. ln of the square root of e. You can do it on your calculator. It should come out fine. Let's be more subtle about it. Let's be more sophisticated about it. Look at that. There's a lot of ways you can get away with this one. A lot of ways you can get away with this one. Tell you what I'm going to do. Is the square root of e the same as e to the 1/2? Yeah, it is. It is. The ln of something exponentiated is the exponent times the ln of that. Isn't ln, logarithmus naturalis, isn't ln the logarithm base e of e? What exponent would you put on top of e to get e? How about 1? Neat stuff. $96. All right, guys, got about maybe 5 more minutes. Do about 5 more minutes on this stuff, guys. I think we'll be okay. Closer. 5 more minutes. Yeah, I think that should be fine. Thank you. Okay, guys. Here they're pulling something on us. Throws a little bit of a curve, not much of one, and don't take it like it's much of one. There are a number of ways you could do this. You always hear me say that. It's a number of ways we can do this. Let's try to make life reasonable here. You got log base 7 of x plus log base 7 of 3 equals 2. They want us to go for it again. There's a lot of ways you can go here. My advice is come back to the bread and butter. Come back here. If it's broken up like this in an addition of logarithmic quantities, which would equal the product of two logarithms, the sum of the logarithms is the logarithm of the product. Say it again. The sum of two logarithms is the logarithm of the product. I condense things, guys. The sum of these two, this is x, this is y, x times y, or y times x, it don't matter a whole lot. Make it the logarithm of a product. Man, that's a lot easier to look at. You know how to do this. You've already done it. If two things are equal and you want to get rid of a logarithm, the only way you're not dividing by the word log. It ain't going to work. If these two exponents are equal, if these two quantities are equal, it's not 7 to the 3x. That 7 is just a bookkeeping thing. It's not 7 to 8. This is just a bookkeeping thing. Don't do a thing with it. The 7 gets significant when you put it down here. This is just bookkeeping. The exponent of 3x base 7 means if you put the exponent of 3x base 7 on top of 7, you get 3x. Say it again. The logarithm of 3x base 7 means the exponent of 3x base 7. It means the exponent of 3x, if you put it on top of 7, you get 3x. Well, here is the exponent of 3x. You're putting it on top of 7. You better believe you're getting 3x. Seven squared, 49. It's that simple. That's all they stayed. You could have done it with, they could have asked other questions, having things exponentiated, then you can take the logarithm on each side. They didn't go that way. Let me not go that way right now. I think you got more than enough with all this stuff, guys. And may it all help you. May it help you as much as possible, okay? So on and so forth. There were two last problems I want to look at. I'm not going to look at them in their entirety, but I am going to tell you some of what I said. Problems 99 and 100, talking about compound interest and getting the final amount. I'm going to write a couple things down related to that. And we're just kind of going to leave it at, largely leave it at that. I think I have seen, I'm just going on what I've done with students in the past, you guys. I think I've seen the way they gave the answer, they kind of opted to use A equals P e to the RT rather than A equals P times the quantity 1 plus R over N to the NT. This quantity A equals P times the quantity 1 plus R over N to the NT is the more accurate way to do it for a lot of numbers. When the number of compoundings gets very big, if you do like 100 different compoundings over the course of a year, it really approximates A equals P e to the RT. Let's just do this really. Let me just write it down real quickly. Also from that practice, I just want you to kind of be aware of that. again, it's not an insult to the people that did this and made the key. They're being a bit lax, a bit cavalier with the way they're answering it, arguably. We're not going to, typically, unless n is a very, very big number, you want to stay the other way. And just some of the do's and don'ts on that. The answers are given to you, so just try either technique so you can conform with their answer. If we're going to go there, I'll be pretty explicit what I want you to do. At least explain the difference. So let me just show that one more time without actually doing these problems, because you can sit down and knock them out and get the answer. But I was going to tell you a couple do's and don'ts on that for the next few minutes, and then we'll kind of leave it at that. All right, guys. You know, in the last part of the old number 3, there's problems 99 and 100, and they're okay. I mean, they're good. And again, the way they gave the answer is not something that's, gee, it's horrible or whatever. But I'm just going on memory, guys. I haven't had a chance to look at it exceedingly closely. But I think on one of them, they opted to show it in a particular way that's a halfway decent approximation to what is happening, but it's not really exactly what's happening. So I don't know. You can argue that. You can argue that a lot of ways, I guess. What's appropriate, what's not, what they're looking for. Perhaps when they were doing this, they were asking people to do it in a particular way. Use one of those formulas that I gave you guys some time ago. So let's figure that out. They're showing problems 99 and 100, so just be careful. I think I saw something that was a bit concerning with it, but they're saying, you guys saw me go here already. I mean, we talked about A, the total amount, and that's the principal, the initial investment, 1 plus R over N. R is converted to a decimal or a fraction. Not percent. You got to take the percent and make it into a decimal or a fraction. And you got this. And we said that A is final amount. P is initial investment or initial loan. Call it the principal. P for principal. R equals yearly rate. If they give it to you in percent, convert it to decimals or fraction. T is time, N is number of times compounded. Number of times you're going to do the bump up in money. Number of times you're going to apply the interest rate per year. Number of times that you're going to apply the interest rate per year. Number of compoundings per year. And we can argue this a bunch of ways. There's other ways you could have a different kind of like master time frame. You could have like a new year, a year on Mars, let's say, or something, or whatever. There's different time frames you could use. Number of times compounded or number of compoundings. So I did spell it right initially, but number of times compounded, right? number of compoundings per year. T number of years. True, period. If, and I think they did something here. They actually used this one. Some people have used this one sometimes. Technically, you shouldn't do it unless it's some really special circumstances, and I'll get into that a little bit. This right here, as simple as it looks, is derived. This right here, as simple as it looks, is derived from here completely. If the number of compoundings per year is very, very many, if the number of compoundings per year is very, very many, then it goes to here. What happens is, in the limit, some really beautiful mathematics that goes into it. If you took 1 plus, and this is good for a lot of stuff, economics, physics, chemistry, you name it. The exponential function is hugely significant. If you took the quantity 1 plus r over n and took it to the n, and then n went toward infinity, the number of compoundings per year went toward infinity. If n went toward infinity and n went toward infinity right here, then the quantity 1 plus r over n taken to the n as n goes to infinity would be e to the r. E to the r to the t is the exponentiation of e to the r to the t power is e to the r times t. It would become p e to the r times t a. It would go to here. If n is really, really big, this is a good approximation. If it's not, then that is not the best approximation, but it's still an approximation. That's all. I just want to tell you that. Another thing, when you're doing it using either technique here, ladies and gentlemen, when you're using either technique here, same with this right here. When you're using either technique here, make sure, for this example, make sure you're going here first. Forget the p. Don't involve them yet. Go 1 plus r over n. Get an answer. The answer of 1 plus r over n, whatever the answer is, whatever the answer of 1 plus r over n is, that answer will be taken to the nt power. When you get that answer, then, and only then, you multiply by p. Do not take p and go p times the quantity 1 plus r over n. Get an answer, and then go to the nt. There's usually not enough money in the world to cover what you calculated. I wish interest was calculated that way. It's not. Okay, one more time. The p is the principal. Don't touch it. Take the quantity 1 plus r over n. Get an answer for 1 plus r over n. Get an answer, and then when you get the answer for 1 plus r over n, that answer and that answer only is taken to the nt power. When you're done with that, then you multiply by p. Same thing here. Take e to the rt, get an answer, and then multiply by p. All right, so just watch out for that. Do this, practice it, you can get it. The answers are given to you at the bottom or in the answer key there, and I think they did something there, so maybe come back here and maybe do it their way to see that they got that answer. Not that I agree with that answer. If it's anything short of infinity, this is strictly the best way to do it. Man, if n is big enough, however, it very quickly approaches this. Very, very important. All right, you guys. That is everything I wanted to say. That should be a good, that's, if you play your cards right, the lion's share of just about any algebra course, short of college algebra, which goes a little bit further, does other stuff too. But a lot of what you're going to find in even college algebra, we just did. A lot of what you're going to find in a lot of algebra we just did. And especially in intermediate algebra, it's almost all here. Very few things are not talked about it. We did the major stuff that we're supposed to do in practically any basic algebra class. The material that we covered here is going to help us with a lot of the basic algebra that we see in an algebra course, in a physics course, in a chemistry course, in a little basic engineering course, something. This is good stuff, guys. It's not good stuff because I'm saying it. It's good stuff because the mathematics is really good stuff. And the guys who did this stuff in the ancient world and in the Middle Ages, they knew a lot of what they were talking about because algebra is used in so much of mathematics. You're not getting in the most highest mathematics that there is, or very close, just very high level mathematics. Somewhere you're going to do some algebra. And that's what we're practicing here, and it's so important. So use it as much as you need to use it, guys. Thank you. I wish you the best. This semester and all subsequent semesters, okay? Thank you.